So, hello everyone. Today I will start with a new lecture, Wettability, in the module 2. So, in the last lecture we discussed about surface energy and surface tension. We defined the surface energy or surface tension in terms of work done or in terms of free energy changes for the change in the per unit interface area. Then we discussed the thermodynamics of the interfacial energy. Then we specifically discussed if there are two immiscible liquid, then how this interfacial surface tension is referred as the interfacial tension or interfacial energy. Also we discussed the interfacial energy between solid liquid interface. Then we calculated the work of adhesion. So, in today's lecture we will be discussing how do we define wettability, or you can say how we define a surface, whether it is hydrophilic or the hydrophobic. Then followed by that we will see how the wettability and the spreading coefficient are related. Then later on we will see the effect of various heterogeneity, chemical heterogeneity as well as the physical heterogeneity on the contact angle or wettability, and in the last we will see contact angle hysteresis. So, to start with, what is wettability? As the word suggests, it is going to wet a surface. So, if something is wetting a surface, if you put a drop of liquid, on the surface, so you may have different aspects. So, one aspect may be it is formed a film, other aspect may be it is partly wetting, another aspect may be it is completely non-wetting, it is forming a sphere on the surface, it is completely non-wetting. So, we can have these three aspects, and for this how do we define this phenomena is called the wettability. Now, if you want to define or express this phenomena, then we can define in terms of if you are putting a liquid drop, what is the angle between the surface and tangent of the liquid. So, based on this angle we should be able to define different phenomena happening on the surface. So, if you just see, there are three interfaces here. The first interface is solid vapor interface, second interface is, let us say you are putting a liquid. So, liquid vapor interface, and third interface will be the solid liquid interface. So, here we are dealing with the three interfaces, solid vapor, liquid vapor and the solid liquid interface, and depending on the value of theta or the contact angle. So, if it is 0, first case it is completely wettable, if it is less than 90, it is partial wettable, and this surface is called hydrophilic. And if contact angle is more than 90 degree, then it is non-wetting surface and called the hydrophobic surfaces. So, we can say the wettability we can easily define in terms of contact angle, and depending on the contact angle we can classify the surfaces, whether it is a completely wettable surface, partial wettable surface or a non-wettable surface. So, we can say it is either hydrophilic or the hydrophobic. So, as we see this is a three interfaces are there. So, as you know, the surface tension is the force per unit length. So, if you simple do the force balance over here, so this will be in this direction gamma solid vapor, this is the opposite direction minus gamma solid liquid equal to gamma liquid vapor. If you bring it to the x axis, it will be the cos theta. So, that is it, and this is from here it cos theta will be gamma S p solid vapor interfacial tension or surface tension minus solid liquid interfacial tension divided by the liquid vapor interfacial tension. This is known as the Young's equation. So, if you remember in the last lecture we discussed the work of adhesion between solid and liquid. So, this was defined as surface tension of liquid vapor plus surface tension of solid vapor minus interfacial tension between the solid and liquid. So, if you equate these two expression from here and here, so we can write work of adhesion is equal to gamma LV, and in place of gamma SP minus gamma SL we can write again gamma LV cos theta. So, it will be gamma LV 1 plus cos theta. So, we can see again, if the contact angle is known to you, liquid surface tension is known, we can calculate the work of adhesion, or in either way, if the work of adhesion is known and the surface tension or surface energy of the liquid is known, we should be able to calculate the contact angle. So, we are having a paraffin wax and water contact angle is coming out to be 111 degree. Surface energy of paraffin is given as 25 millijoule per meter square and surface energy of water is 73 millijoule per meter square. Now, we need to estimate the interfacial tension between 1 and 2 water and paraffin, as well as we have to calculate the work of adhesion. Now, if you remember the Young's equation, so Young's equation says cos theta is equal to gamma SV minus gamma SL divided by gamma LV. So, here we can write in terms of gamma 1 and gamma 2. So, gamma SP means gamma 1 paraffin, gamma SL means gamma 1 2 divided by gamma LV, liquid we are considering gamma 2. So, from here theta is known, we should be able to calculate what will be the value of the gamma 1 2 will be gamma 2 cos theta minus gamma 1. So, if you calculate, so it is coming out to be the 51 millijoule per meter square. Now, if once we have calculated the gamma 1 2, then we can easily calculate the work of adhesion. W12 will be gamma 1 plus gamma 2 minus gamma 1 2. So, it will be like 25 plus 73 minus 51. So, it will come out to be the 47 millijoule per meter square. Now, if you remember the last class, we can also calculate the gamma 1 2, even the contact angle value is not given to you, or you can say the work of adhesion you can calculate, even the contact angle value is not given to you. So, if you remember the last class, so the work of adhesion W12 will be twice of the gamma 1 gamma 2 to the power half. Now, we discuss the surface energy have both polar and dispersive components. So, it was like 2 into gamma 1 p gamma 2 p to the power half plus twice of gamma 1 ka dispersive gamma 2 ka dispersive to the power half. Now, paraffin we can assume it is a non-polar. So, its polar component will be 0. For water, it is having both polar and non-polar component. The polar component is higher 53, non-polar is about 20. So, this term will be 0 because the paraffin does not have any polar component. So, W12 will be simply twice of the gamma dispersive of paraffin, we can say exactly 25 into water 20 to the power half. If we calculate, we will get very close similar value as we have calculated 47 millijoule per meter square. So, we can calculate the work of adhesion even if contact angle is not known. That is why we discussed in the last slide. From we can interplay between these parameter, work of adhesion, surface energy of the liquid and the cos theta. So, this was the example. We can calculate the work of adhesion or interfacial energy from the contact angle. Either way we can calculate if only the surface energy of the both the mediums are solid and liquid as known to us. So, we will just see another example based on the same concept. It is claimed that a droplet of a surfactant on a mica surface which have the surface energy of 27 plus minus 2 millijoule per meter square. Liquid means surfactant surface energy is 40 millijoule per meter square and gamma 12 interfacial energy or interfacial tension is 11 millijoule per meter square and contact angle is 64. Now, you need to verify whether the data presented is valid or not. So, the one simple step will be you calculate the cos theta will be gamma 1 minus gamma 1 2 divided by gamma 2 using the Young's equation, and this value will come 27 minus 11 divided by 40. So, this will be like to 16 divided by 40. So, this will be coming out to be 0.4. So, if you calculate the theta is equal to cos inverse 0.4, this will be coming out to is very close to the 65 degree. So, the claimed value is 64. So, it says the data presented is the valid data, or you can say the data agrees with the Young's equation. So, in this way we can interplay between the surface tension, surface energy, interfacial energy as well as the contact angle or the wettability. Now, here what we are going to see there are 3 mediums 1, 2 and 3 and they are coming into the contact. So, in the first upper half in this region what we are seeing is 1 and 2 is coming into the contact, 1 is here, 2 is coming into the contact and surrounded by the medium is 3. 1 is here, 2 is coming which is surrounded in the medium 3. Now, depending on the different surface property, we can observe the different weighting behavior. So, if you see here in case of 1, it is partial wettable. In the second figure, you can say it is hydrophobic. Third, you can say it is completely not wettable. So, if you want to calculate here work of adhesion total adhesion will be, let us say this particular area is the AC and this particular area is the AF. So, gamma 2 3 interaction between 2 and 3, this will act upon the both the surfaces. So, gamma 2 3 will act on the AC plus AF. The gamma 2 3 will act on the AC plus AF, but here it will be the interfacial interaction or work of adhesion between these 3 W1, 3 and 2. Here the contact area will be only the AF. So, W total will be gamma 2 3 AC plus AF minus W123 AF. Now, at equilibrium W total will be gamma 23, you can say dAc plus dAf is equal to gamma 132 dAf. Now, if we just see over here, based on this area, this angle is theta, and you can consider this one area is the AC and this is the AF. So, this is the AC and this is the AF. So, this cos theta can be defined as dAc upon dAf. Here the cos theta can be defined as dAc upon dAf. So, here we can simply, if you divide AF here, so this will be the AC upon AF. So, this will be gamma 23 1 plus cos theta is equal to W132. Now, this is again looking a similar expression as the Young's equation. Now, if you remember the last class, we can calculate the work of addition between the 1, 2 and 3 as gamma 1 3 plus gamma 2 3 minus gamma 1 2. If you put this value over here, if we replace W132 with this, so we will end up with gamma 1 2 plus gamma 2 3 cos theta is equal to gamma 1 3. So, what it says is surface energy interfacial tension between 1 and 2 plus 2 and 3 of the cos theta is equal to the 1 and 3. This is exactly same as the Young's equation. So, in the Young's equation, what did we see is this was a drop, this was the solid vapor, this was solid liquid and this was the liquid vapor. So, what we observed was gamma solid vapor, the solid vapor will be here 1 and 3 equal to gamma liquid vapor 2 3, this is the 2 and 3, gamma solid liquid is here, solid liquid is 1 and 2. So, this is coming out to be same, gamma solid vapor is equal to gamma solid liquid, this angle is theta plus gamma liquid vapor cos theta. So, again from here you just see this is how the Young's equation is derived from this. Now, next what we are seeing in the bottom figure is we are having the interaction between 1 and 3, it is surrounded by the 2. So, here it was interaction between 1 and 2 surrounded by the medium as 3. Now, we are replacing, you can say, are exchanging 2 with the 3. So, if the media 2 is and 3 are interchanged, so it will be like gamma 2 3 1 plus cos theta is equal to, now it will be W 1 2 3. Earlier it was W 1 3 2, now it will be W 1 2 3, and we can similarly define W 1 3 3 will be gamma 1 2 plus gamma 2 3 minus gamma 1 3. So, from here if you rewrite this, so it is coming out to be gamma 1 2 minus gamma 2 3 cos theta is equal to gamma 1 3, or you can from here again you should be able to write this is gamma 2 3 cos theta, this is gamma 1 3. Now, from here again if you want to write in terms of this expression W 1 3 2, W 1 3 2 is gamma 1 3 plus gamma 2 3 minus gamma 1 and 2. So, this expression if you write in terms of, or you can say here we only replace the gamma 1 3. So, gamma 1 3 you will write gamma 1 2 minus gamma 2 3 cos theta. So, it will simply gamma 1 3 will be gamma 1 2 minus gamma 2 3 cos theta plus gamma 2 3 minus gamma 1 2. So, gamma 1 2 will be cancelled out. So, this will be the W 1 3 2 is equal to gamma 2 3 1 minus cos theta 0. So, what it says, if you exchange the medium 1 and 2 in medium 3 and 1 and 3 in medium 2. So, angle will be changed by the theta will be changed by 180 minus theta. So, what it says, the theta 0 what was coming in the first case, it will replace typically by the 180 minus theta. Now, if you go to the last slide, just see in this case it was not wettable, in this case it is completely wettable. In this case this was the hydrophobic, now it has become hydrophilic. In this case was the hydrophilic, now it become the hydrophobic. So, what it suggests, although we are dealing with the three systems, but how they are going to interact, it is going to affect the wettability or the contact angle. And it was very interesting observation that when 1 and 2 are contacting in the medium 3 and when 1 and 3 are contacting in the medium 2, the theta should be replaced by 180 minus theta. Now, next is the wettability and spreading. So, as you remember, very first class we discussed the adhesion and the cohesion. So, if it is going to wet a surface, it means there is going to be the adhesion. So, work of adhesion, if you remember, work of adhesion is gamma LV plus gamma SB minus gamma SL, or you can say, if you remember, W 1 2 is equal to W gamma 1 plus gamma 2 minus gamma 1 2. But if it is the cohesion, so W 1 1 will be twice of the gamma 1. So, this is a difference between the adhesion and the cohesion. So, work of adhesion we know, work of cohesion is known. So, simply the spreading coefficient is the difference between the work of adhesion and work of cohesion, and if you subtract this, so what will be there, 1 gamma LV will be cancelled out from here. So, it will be AS is equal to gamma SV minus gamma LV minus gamma SL, or you can say gamma SV minus gamma LV plus gamma SL. So, based on the difference between this, we should be able to calculate if gamma SL SV is greater than gamma LV plus gamma SL, then S will be greater than 0. In this case, it is going to spread, liquid will spread spontaneously on the surface, but in the other case, if S is less than 0, if S is less than 0 means there will be no spreading or the no wetting. So, we can simply say the spreading is the spreading coefficient is the difference between the work of adhesion and the work of cohesion, and depending on the value of S, we should be able to comment whether there will be a spreading or there will be the partial spreading, or you can say no spreading. Now, next we will see there may be different kind of heterogeneity on the surface and how it is going to affect the wettability or the contact angle. So, first we will consider this is a surface which is having two chemical heterogeneity. In one case it is behaving a hydrophilic, in other case it is behaving as the hydrophobic. So, if the surface is a mixture of these two, so how it is happening, just see here. If you specifically zoom at this area where it is having surface is having the mixture of these two moiety. So, it is going to the contact angle from here hydrophobic, it will slowly go towards the hydrophilic. The wettability will be the intermediate between the two chemical moieties. So, considering this, or you can say this surface energy will have the contribution of the surface energy of one as well as the surface energy of the two. So, you can say the cos theta will be the whatever fraction is coming for 1 f 1 cos theta 1 plus f 2 cos theta 2, and this is known as the Cauchy equation. So, Cauchy equation says the total surface energy is simply the sum of its constituents. F 1 the fraction of 1 here, and F 2 is the fraction of the 2. So, whatever, so let us say if a surface is made of two different groups and the fraction of one group is known to you, you should be able to calculate the fraction of other group if it is says it is completely covered. If you completely covered means it will be like f 1 plus f 2 is equal to 1. So, if f 1 is known to you, you can calculate the value of f 2, and for this individual contact angle should be known. You should be able to calculate the contact angle on a mixed surface, contact angle on a mixed surface. A surface is having the different chemical heterogeneity. Now, let us say we are going to have now the physical heterogeneity. Physical heterogeneity means simply you can say you are having either a rough surface or the textured surface. So, textured surface can be randomly rough, or you can have a particular texture, or you can have a periodic profile or a particular pattern. So, in this case, if it is a smooth surface, you can write smooth and rough. If it is the rough surface, it is going to have different wetting property. Why it is going to have different wetting property? Because in case of irregular surface, molecular, or you can say the real solid liquid contact area is not the same as the macroscopic area, or you can say the projected area. Because let us say you are having a surface like this, this is the rough surface. So, whatever area was from this surface, the rough surface is going to have the higher area. So, if you remember the Young-Dupré equation we discussed in the last class. So, we can simply modify that the work of adhesion here is equal to gamma L 1 plus cos theta multiplied by a factor of the RF. RF is known as the roughness factor, or you can say 1 plus cos theta is equal to the RF times WSL from the Young's equation. If you just say from Young's equation, WSL is equal to 1 plus cos theta 0. So, this is the theta on the rough surface, this is the theta on the smooth surface, and this roughness factor is simply defined as the what is the actual area and what is the projected area. So, if you compare this expression, end up with cos theta is equal to the RF cos theta 0, if you multiply the roughness factor with the actual contact angle. So, cos theta is simply the, if you multiply with the roughness factor, and roughness factor is the actual area divided by the projected area, and it is a dimensionless number. Now, if we just see over here, this is also saying the same thing. Let us say this is not a flat surface, this is a smooth, not a smooth, sort of rough surface. So, if we just see here, the contact angle will be theta 0, again here if you go for more higher, then theta will be less than theta 0, again theta 0. If you go further on the belly, or you can say heel and belly, then theta will be again, now it will be greater than theta 0. Then if you come to the same level or same surface, it will be like a again theta 0. So, we are going to have lot of transition between the contact angle because of this textured surfaces. It may have the randomly rough, it may have particular texture, it may have periodic profile, it may have a particular pattern. So, cos theta of the rough surface is RF times the cos theta of the true or the actual surface. Now, if we can have different value of RF value can be greater than 1, it can be less than 1. If the RF value is greater than 1, then theta will be lower than theta 0, and if RF is less than 1, it means the theta will be higher than the theta 0. So, what it says, the liquid solid adhesion per unit projected area must be higher or lower depending on the value of the roughness factor. So, the solid liquid adhesion per unit projected area can be tuned by tuning the roughness factor. So, we will see how a surface can be made more hydrophilic or more hydrophobic with having the same chemical nature by simply tuning it the surface morphology or the surface roughness. So, in case we will consider one case where RF is less than 1. So, if RF is less than 1 or your initial, or you can say the true theta 0 was less than 90, it was a hydrophilic surface. If you contact angle decreases if you increase the roughness, it means you are increasing the more contact area, you are going to have the more wettable surface, or you can say surface will become more hydrophilic. But if your initial contact angle is more than 90, then your contact angle will increase with increase in the roughness. So, what it says is, if it is a hydrophilic surface, if you increase the roughness, it will become more hydrophilic, but if it is a hydrophobic surface, if you increase the roughness, it becomes more hydrophobic. So, we can say again there is a effect of roughness, but the effect of roughness factor is again dependent on the what is the initial value of the surface wettability. If it is hydrophobic, it is going to behave differently. If it is hydrophilic, again it is going to behave differently. So, here let us assume we are having a pattern surface. So, let us say this is you are having a surface structure, it is having this kind of structure. So, if we draw a 2D profile, so 2D profile will look like now we can try to complete this. This is a 2D profile. We can make a wave pattern like this. So, from this surface topography or surface morphology, you should be able to draw a wave pattern. So, this is the same wave pattern here. going like this to this, fine. So, we will just consider one wave pattern. So, what we are going to do, this one wave pattern we are going to complete a circle with the radius of the r, and of course, once you are measuring using some techniques like atomic force microscopy or ellipsometry, we are going to know the value of R A will be known, what is the average height will be known. Now, if you consider one wave, as we are considering the wavy profile, one wave average wavelength, also we are considering lambda from here to here, we are considering the value of lambda A. Now, once we have formed the sphere and this angle is the theta. So, and theta is simply the length of arc upon the radius. So, length of arc will be here AC, here will be BC. So, length of arc will be r times theta, and if you consider the ACB, it will be simply like the 2 theta. So, you can say ACB will be the arc length from here to here, ACB will be twice into r radius into the theta. Now, if you want to calculate the value of theta from here, you should be able to calculate, this length is known, this is the x, this is the r, you consider this as a 90 degree. So, we simply calculate sin theta will be x upon r, sin theta will be here, sin theta will be x upon r. So, we should be able to calculate theta is equal to sin inverse x upon r, and if you want to calculate the r, if it is again considering as this is as a 90 degree. So, if you apply this theorem 90 degree, so it says that r square is equal to x square, and this length is again r minus r a. So, it says r square is equal to x square plus r minus r a का whole square. So, this will be simply x square plus r square plus r a square minus 2 r a. With the cancel out. So, we will simply get the value of r is equal to x square plus r a square divided by 2 times of the r a. So, here simply if r a is known, we should be able to r a and x is known, we should be able to calculate theta as well as the r. Now, what is the perimeter of one wavelength? One wavelength is lambda, if you just see, it is twice of the ACB. So, twice of the curve length ACB. Now, let us say total length is the L. So, how many waves will be there? Number of waves will be the L upon the lambda A, length of one wave. So, the complete profile parameter will be P will be, let us say complete profile parameter we are calling P, it will be the how many waves are there? L upon lambda A into P, P will be the twice of the length of arc ACB, and ACB is the 2 r theta. So, it will be the 4 r into theta, and theta is the sin inverse x upon r. So, it is like 4 L upon lambda A r theta, and theta is equal to sin inverse x upon r. So, now if P is known, P is the projected perimeter, this was the L and projected length is, this has increased to the P, L has increased to the P. Now, if you can consider as a rectangle here, the projected area was L square, actual area will be the P square. So, simply in this method, this was one example how we can calculate the value of the roughness factor. So, next we will see the contact angle hysteresis. So, if there is a surface, you are putting a drop of the liquid. We used to in one case, once you are putting the liquid, other case you are the pulling out from the surface. So, when you will put the drop, when you will pull out the drop, there is going to be difference between the interfacial interaction between the surface solid and liquid. So, here if you are putting the drop, contact angle is the theta a, that is called the advancing contact angle. If you are pulling the liquid out from here, the contact angle is called the receding contact angle. And because both are not the same, typically advancing contact angle is higher than the receding contact angle. It says this system or the solid liquid interaction is not in the equilibrium, that is why it is called the metastable non equilibrium state. And this hysteresis on heterogeneous surface is due to the free energy barrier between the different wettability regions. So, this may be the one option ki here and here we are not going to have the same free energy, and the advancing angle determined by the surface region with lower wettability, while the receding angle determined by the surface with the higher wettability. So, again it says there will be the difference between the contact angle, or you can say the advancing angle and the receding angle, and advancing angle says lower wettability, while receding angle say determined by the surface with the higher wettability. So, if we are performing this contact angle hysteresis on the surface and we are seeing a significant difference between the advancing contact angle and receding contact angle. So, it says there is a heterogeneity on the surface, and the first thing we can infer is that there is a surface heterogeneity. It may be the physical heterogeneity, it may be the chemical heterogeneity, but ultimately it is coming because difference in the free energy. It may be the change in the chemical or the physical nature of the surface after they came into contact with the liquid or another material, or the other option may be there is some adsorption is taking place. Once you put the liquid drop, what is happening, there is some adsorption is taking place on the surface. So, if adsorption is taking place means surface energy of the surface is changing. Once the surface, if you change the surface energy of a surface, again its wettability is going to completely change. So, these are the few aspects. If you perform the contact angle hysteresis, we should be able to understand, or you should be able to comment on the surface heterogeneity, you should be able to comment whether there is some change in the some adsorption pattern or not. Also, we should be able to see what is the chemical and physical nature of surface when they contact into a liquid, or it may be some other material. So, here we conclude this lecture. So, what we discussed today is the wettability. Wettability we simply define in terms of the contact angle. If you put a drop of the liquid on the surface, it may completely wet a surface, it may form a certain angle less than 90, we call it a hydrophilic surface. It may be more than 90, it means it is not wetting the surface, it is called, we call the hydrophobic surface. To define this process, we calculated the difference, or we equated the interfacial tensions, and we derived the Young's equation. So, Young's equation relates the interfacial tension between all three components, gamma solid vapor, gamma solid liquid, and the gamma liquid vapor. And then we saw the effect of physical heterogeneity, especially in terms of roughness. We saw the effect of chemical heterogeneity, especially we are having the mixed surface or mixed moieties, and in the last we just see if you are performing the contact angle hysteresis, it is a meta stable non equilibrium state and infers about the surface heterogeneity or adsorption of a compound on the surface, so that there is some change in the solid surface energy. Thank you.